on a criterion called Routh-Hurwitz criterion. So the system we say is bounded input, bounded output stable or BIBO stable. If we apply a bounded input, we expect to get bounded output. We say the system is BIBO stable. Based on mathematically, if you look at the roots of the denominator of transfer function, if its poles or the roots of the denominator will lie in the left half plane. And we understand why is that. Why, if the pole in left half plane, the system is stable, and why, if it's in the right half plane, not. But we will review this in a minute. So let's look at these examples, and please share your ideas with me. If I have system has these 3 poles, do you think the system is stable or not? Is it BIBO stable or not? These are the poles. This is the left half plane. This is right half plane. This is the imaginary axis. That's the real axis. So this is the complex plane, right? Is the system BIBO stable or not?
I'd say stable.
Yes, correct. Online. Anyone here? It is. It is BIBO stable. All right. If I have system like this, is it BIBO stable or not?
We're not allowed to have poles in the real region, are we? Or in the positive region?
Yes. Yes. Yeah, you are correct. So this is not BIBO stable. How about if I have system that has poles for locations like this? Is the system BIBO stable or not?
No.
No.
Here in class? No. Not BIBO stable. Because this will keep oscillating all the time. Remember the response? For this guy, that will make it go up there. Right? So BIBO stable, BIBO stable, not BIBO stable, not BIBO stable. All right. All right, so that's based on the following facts. So let me review this fact as background for Routh-Hurwitz criterion. All right, so background for this, or review about some facts that we learned so far. So first, if we have transfer function h of s, that's the denominator and denominator is polynomials. So this is the n of s is numerator polynomial, denominator polynomial. But specifically, this is what we call it the characteristic equation. Characteristic equation. Why? It tells us a lot about our system, because the roots of this equation are the poles, and the poles tell us if the system is stable or not, or how the system will behave. Even if it's stable, still we can read many or see a lot of information by looking at the locations of the poles as well. So this is called characteristic equation, which is the denominator equation. So let's say that they have a like simple transfer function, h of s equals 1 over s plus a, where a, this just variable. All right. So if a is positive, greater than 0, if a is positive, that means s will be negative, right? And that pole will lie in the left half plane. Do we agree on this fact? While if a is negative, that means s will be positive, and our pole will be in right half plane, right? So if I plot here the complex plane, here's the real part of s. These are curly brackets. And here the imaginary part of s. So for my system to be stable, to be in the stable region, all poles needs to be in the left half plane. So this system will be stable, but this system won't be stable. And that comes from the following fact. If I find Laplace inverse of H of S, from here, it is just from the table, E negative AT, where this is the root, right? This is the root. So if I plot that in here, so if A is stable, A is positive, S is negative, the pole is in left half plane. So the response of that system will be something like this, at 0 equals 1, and then start decaying. So it's bounded output. That's bounded output. While, let me use the same color for this guy. So this is negative, that means S is positive at 0 equal 1, and then as the time passes, this will go to infinity. So that's why we say the system is unstable. Is the idea clear? All right. So if I have another transfer function, that's H of S equals 1 over S plus 1 times 1 over S plus 3, 1 over S minus 2. So let's say Laplace inverse of H of S will be something like this. E negative T plus E negative 3T plus E positive 2T, right? So if I plot these three, so this is T and this is my function or the magnitude. So I represent this with red, this one with blue, this one with black. So for the one that's shown here in red, so if let's say that, oh yeah, it will be start at 1. Let's say, you know what, let me do this just to make it different. Not when I plot them separately. Let's say this is equals 2 here. So that here will be 2. That does not affect the stability. That's gain, not related to the stability, right? So this guy at 0 equals 2. So as time passes, it will be decaying, right? As t goes to infinity, that will go to 0. The second one, maybe decaying faster. This is higher number, and at 0 equals 1, right? This may be slower. All right, while this guy that I will draw in black, this guy, at 0 equal 1 as well, right? Here. And then it goes to infinity. So obviously, this pole made my system unstable. Even though these two are stable. So when we look at all the pole all poles locations. All of them should be in the left half plane.